In this episode, I talk with biologist and computer scientist Hananel Hazan. What it's focused on is applying computation to biology. How can we use computational methods like machine learning and neural networks to understand biology? And also, how can we learn from biology and its seemingly complex computations and apply that to other areas? I hope you enjoy. Hananel, it would be great if you could say hi and introduce yourself a bit, and then we can get straight into this.
So thank you for inviting me to your channel, Jack. It was a great collection of people that you already interviewed, and I'm happy to be here. I'm a computer scientist, specialized in bio-inspired machine learning. I did my PhD in University of Haifa, supervised by Professor Larry Manevitz. And since my PhD, I started to work on a way to take what we know in machine learning, in neural network, more precise, and take it to more toward the biology side, what we can use and we know from biology in order to improve our understanding in machine learning in a way. Since then, I did a postdoc in the Technion in Shimon Marom and Noam Ziv laboratory, where I was working to create a software or a framework to make a closed loop between cortical neurons that planted on a chip, and they are communicated with computer, and the computer sends the activity of those neurons and try to stimulate one of those neurons or one part of those neurons in order to close the loop between the two, creating some sort of a feedback, real-time feedback system. It was great work and great experience. And I then moved to the US to do a postdoc in UMass Amherst in computer science, this time out of the biology. And during that time in the Bynes lab, at that time under the PI was at that time Robert Kozma. We worked on a grant of DARPA to create network of spiking neural network that are stronger or faster than what we can do with regular machine learning. We end up creating a framework that called BindsNet, and that's framework that based on the foundation of PyTorch, the library that we use in calculating machine learning today. And that framework gives help to any researcher that would like to work with spiking neurons and not only the regular neurons. A way of tools to create, work, and analyze how to work with spiking neurons. These tools get huge popularity. Actually, it's the first one on the category of spiking neurons in GitHub. And that's without the help of the students that helped to create that framework. It wasn't not possible. For example, Daniel Sanders, Darpan Shrigevi, and as I mentioned, Robert Kozma, the boss, and Chava Sigman was the boss at that time. So after I spent the time on working on computer science, I thought, okay, I did computer science, biology, and computer science. Now it's about time to go to real and to work on my own, on combine both of those two aspects. So I came up with Professor Levin laboratory, and I now try to make both of the computational side and the biology side, both of them together.
Yeah, awesome. Yeah, thanks for that, Hananel. And just to touch on a couple things, because it will kind of, or that you said, because it'll kind of foreshadow things we'll talk about later on, as you talked about spiking neural networks and how their improvements over more ordinary kinds of neural networks and machine learning algorithms that we have today. So that'll be interesting. And also, did I get this correctly? You kind of, not only are you applying machine learning and things to model biology, but you're also using biology to learn from biology itself to actually improve the computational side of things. Is that right?
Right, right.
Very,
It's both direction.
uh-huh.
I'm using the tools in machine learning to try to help biologists to understand how cells communicate between each other, what's the difference between
Mm-hmm.
cells when they apply some medicines, what kind of interaction that they can expand. And for that, we can use classical machine learning tools in order to understand those phenomena. On the other hand, the information that I'm understanding from those experiments with the biologists, I'm trying to take those information and try to improve some sides of some
Mm-hmm.
subsets of machine learning to make it much faster or
Uh-huh.
robust or in different ways. So there are many things that we can learn from biologists.
Mm-hmm. Very interesting. Well, before going like sort of in that direction, I'd be very interested to like start from the beginning and just even like think about what and when did people start thinking that that biology could be modeled through computation? Do you know like the earliest time we started thinking like, hey, maybe we could actually try and use maybe not even machine learning algorithms? Like when were we first thinking about trying to model using computers biology?
Oh, okay. So it's a great question. I'm not sure exactly when
Mhm.
exactly we thought about that, but I know, for example, Turing itself, Alan Turing itself,
Mhm.
was very, on his one hand, invent the universal Turing machine and the computers as we know it today. On the other hand, work on biotoxins and diffusion reaction in cells and create the Turing patterns, the one that we saw on zebra or
Mm.
other animals that
Yeah.
have some patches. So those kind of patches are mainly the signature of Alan Turing. So he also thought already at that time on the implementation of universality and the way that cell communicating and sort of, and that also goes to Shannon Cloud's theories on information theories. He also was very interested in biologies.
Mhm.
But in a way, if you can look at that, I think at the first time that Hodgkin and Huxley simulate the first neuron, and they got a Nobel Prize on that
Ah.
simulation. If I'm not mistaken, they somewhat around the 50s that they simulate the Hodgkin-Huxley. Um, and from that time, or actually, it's 1963, actually.
Mm.
So at that time, people in computer science already saw that kind of invention and say, wait a second, we can use it. It's a basic cells that doing some function, and that function can't be used to do some computation. I think it was already visionary at that time to look at that. And
Ah.
from that point, in 1969, we can see already the McCullough-Pitts neuron, the first neuron that all of the artificial neural network is based on. And that
Mm.
simulation was one single neuron that can perform a logic function that already been known that it's not going to be a universal Turing machine because it's unable to perform XOR or
Sure.
other complicated function. But as a one unit, as an individual unit, it's already been proven that it can learn, adapt its weight to the environment and producing a different function. So
Very
that's, I
interesting.
guess, the history.
Yeah, that's no, it's a helpful answer. And you don't need to, Google things to get the exact dates or anything. That's and as that comes sort of like towards the present day, we hear like a lot about like especially with large language models at the moment. And I know like the things you use to model biology can often be quite different to those. But like when do we start using like kind of more modern machine learning, and maybe you could even explain like how it works and like why anyone would even think that it could model biology. Like in what ways does it work?
Okay, so basically, most cells in the body, or especially in the neurons, are taking the information from the surrounding, the environment, calculating something. They have some function inside, and producing an output decision what to do based on that activity. For what we can see that starting from that kind of a perceptron and multi-layer perceptron, the computer scientists already noticed that this neural network can produce or can mimic any polynomial continuous function. And that is a powerful tool. So it means that based on your input, you tune the weights of the neurons in order to mimic every other function that you can find and you can describe. Using that kind of tools that open up a lot of other options to utilize as a tool in computer science and on our understanding on what cells do in biology. Although the boundaries already been questioning about that. That will be the gray lines here, because at the beginning, at least, the Macaulay-Pitts neuron was contain some certain of features that are not present today, only because they were already being geared to be tuned to the neurons that been in biology. For example, and that will be maybe jumping ahead, that will be the main difference between spiking neurons to the analog neurons that we know today in most publication and most companies that use. The analog neuron are input and output, and every iteration that it take the input, it calculate a function, and it produce an output. So the function can be sigmoid, can be tangens, can be ReLU, whatever function you can put. But the main point is that every iteration you have an output. Compared to spiking neural network or spiking neurons, based on the fact that neurons operate on 0 and 1, spike or not spike. And not every input produce an output. Actually, it's opposite around. Most of the inputs produce completely zero output. And even more to complicated stuff, neurons or spiking neurons are accumulative, meaning they take the input. If they didn't produce an output, they remember the current value of their activation to the next iteration that they have. So they're accumulating the input until they pass the threshold. So it's not really accumulating, it's not only accumulating, there is also a decaying function, constant that exists. So it makes the neuron forget for a moment.
I see. So it's interesting that you went from there to the sort of seemingly more complex spiking neural networks, but that can sort of maybe better model biology. But before we get there, I'm interested in, like, since with machine learning, even though maybe it sounds complex to other people, in some ways I think about it as, in a way, it's as you're kind of talking about, sometimes it's a bit simple, right? You just have weights but connecting different levels, right? And that's not exactly actually how biology works. It's like a nice mathematical simplification. So I'm almost
exactly.
So I'm on that sense, I'm kind of wondering why, to what degree has current frameworks using the kinds of weight-based neural networks that have been so prevalent, to what degree are they effective? To what degree do they work? Because sometimes I'm like, wow, biology is so complicated. So how actually effective are they at modeling it? Would you be able to speak at, like, because it's hard from an outsider to think, actually, like, okay, we're using this complicated computer science to try and model biology. How well are we doing? If that makes sense.
It's a complicated question, and also it's a complicated answer. Let me unpack it a little bit. there are many simplification that done in when they computer scientists take biology to make the model. Those simplifications are eventually needed because not everything that exists in biology are required to the computational side. For example, if all we care is the voltage of the neuron and the way that it's accumulating input, we don't really need to know exactly the number of ion channels exist in the cell in order to calculate it. Moreover, we don't really need exactly to calculate the exact diffusion reaction happen inside the cell in order to calculate that thing. You are right that it will give you much order of accuracy in the calculation, but if all you need is the voltage, there are a lot of things that you can read off in order to make the computational more easy to other machine to calculate. So in a way, you're right, machine learning in computer science are much more reductionist approach to biology. But in that direction, moving to that kind of direction, it's very easy to throw the baby out with the water bath. That's the problem with that kind of aspect. So in a way, artificial neural network is way more simplification of the biology side. And they are trying to say, you know, there is a lot of low details that are not really matter. What matter is the computational side of things and how things are working between the information exchange, how things work. Maybe it's not the exact way that the human brain works, or maybe that's not the exact way of how the visual system work, but roughly it should be like that. That's how the calculation be. Again, only because we reduce a lot of low-level information that we reduce. So in a way, it's helping for both sides. You would like to see the 10,000 point of view on a biological system. That's the way to go. And also in industry point of view, machine learning is a huge breakthrough and a huge tool to use today in everything that we do. So it helps for both sides. But once you come up to little bit lower level to the biology side and saying, wait a second, neurons are not connecting between, they are not transmitting real numbers between each other. They're transmitting spikes, they're transmitting one and zeros. Not only that, the connection between neurons are not bidirectional. Mostly it's one directional. And on it, even more than that, synapses cannot flip sign. They cannot change polarity. They either inhibitory or excitatory. All those factors are completely peeled out in artificial neural network. In spiking neural network, we try to keep those features exist today in order to be more truthful to the side of biology if we try to understand what biology is doing. So there are some things that you say, oh, that's not acceptable, but that is acceptable. But it's depends exactly what point of view you would like to see it.
So if I'm getting you correctly, right, we've used for a long time sort of machine learning and neural networks with these weights, and in a way it's a mathematical simplification. I would love it if you could now maybe go into and fully explain why we would want something like spiking neural networks, how they're different, and also one thing is, you know, with spiking neural networks, when you can make things sort of ones and zeros and work more like how biology works, in some ways it sounds more simple. It sounds like
right.
And it's I don't know if that's like a kind of dichotomy or you know, so there feels like to me is some kind of like an unexplained factor there of why we would want to use that. So yeah, I would love if you could talk about that.
Okay, so as always, there are more than one option to look at it. You would like to use spiking network also because there are some simplification that we've been reducted from the standard classic neural network. And those simplification being reducted because in order to make the mathematics and the way that we analyze in the way of mathematics analyzation of the neural network, or the way that we tune the weights, like with backpropagation, and more tractable, much more easier. If we add more complication, like for example, threshold, we can completely mess up the backpropagation algorithm.
I see.
If we add the fact that synapses are not connection bidirectional, backpropagation is not able to work in more simplific way. So there are some version of backpropagation that are able to work. But to your question, why we would like to have that? So first of all, if you would like to make computers much more reliable and much more simpler, you would like to operate as 0 and 1 and not as a real value that communicate between each other. More than that, in a way to calculate today input and output in neural network, in artificial neural network, you need to calculate a huge vast of matrices and vectors, and to produce a huge another vectors, and all the time producing a lot of vectors. So the bandwidth that you need to communicate between the units is enormous. On the other hand, in spiking neurons, most of the input doesn't produce any output. So the communication between neurons are much, much simpler and sparse. And even with this, we're able to do the calculation. So there is a lot of claims about reduce connectivity, reduce communication line, simplify the hardware that require in order to make the neurons operate. And most important, energy utilization. With all the implementation, if spiking neural network will implement it in hardware, the computational resource or the computational power of that unit will be compared to the power that it requires. It's enormous. You can't even the computational comparison is between your brain, for example, that take only 20 watt of power. That's our goal standard for our computation. And we are not able to reach to that kind of computational or versus power resources in our regular classic computers.
Right. So are the spiking neural networks, do they require more energy? Are they than previous ones? Like, are they because I'm hearing this thing where, like, in some ways they're more complicated than our previous ones, and that's why some people have turned away from them. But then in another way, are they more effective? Like in terms of like a modeling perspective, are they like in some way more efficient?
Right. So in a way, both of the neurons will require to sum up the inputs that come to that neurons. Both of artificial neural network and spiking networks will, as a unit, they need to sum up the value and produce an output. In the artificial one, they produce output every time. So every iteration, all the units produce an output. In spiking, not every unit produce an output. So it saves a lot of communications between the neurons. More than that, the computation inside the neuron itself, if it's not passing a threshold, it's accumulating and saved to the next iteration. It's been easily to simulate that with a capacitor. It's just a capacitor. You don't really need to calculate everything. You can use an analog devices that are much simpler in order to calculate such a phenomenon.
Okay, that's very helpful. So actually, in some ways, they're more efficient energetically, and so does that get to where you're talking about the start of actually learning from biology and then thinking about how could we make like computation just more effective in other fields, like as we apply it elsewhere. Very interesting.
There is a lot of papers in the subject that adversarial learning or adversarial attacks on neural network, regular neural network, artificial neural network, are much more effective compared to the same adversarials on a spiking neural network. Spiking neural network are much more robust to interference in the input itself and the resiliency inside the network itself. For example, some of the neurons can be some stop to work, and still you can calculate the output of the system. It's something that is not possible to do in an artificial neural network currently now.
I see. I mean, from at this point, maybe it would be let me know if you think this would be interesting if like you could speak about like one instance, like or one paper where you've applied spiking neural networks to like try and model biology. I think about like the one on bioelectric networks and the large scale complexity, and how and why we might want to like use spiking neural networks to try and sort of understand that.
Okay, so one paper that I did in UMass Summers with DARPA Srinavi, we tried to mimic. At that time, Google announced that it can create a network that play Atari game in a superhuman capabilities, much better than every human that capable to play a Atari game. And we tried to take a neural network, a spiking neural network, and train that neural network in order to at least get near that performance of Google. Again, get the main drawback of spiking neural network is not reaching to the potential or the ability that regular neural network achieve, only because of backpropagation. We don't really know exactly today how to use or to train spiking neural network in an efficient way to reach to that level. But we can, for example, take a network that's been trained with backpropagation and convert it to a spiking neural network with the same weights and play with the same game and neural network. And we end up playing the same game, reaching sometime better and sometime worse than, but in a way, in average, it will be a par to the network that's been published by Google. And that's first, the network use less activity in the network. So every frame that you pass to the network produce less activity on all of the layers of the input. And moreover, when we intervene in those layers, we disable some of the neurons, the network still operate, which the neural network, the artificial neural network, in the same intervention will be catastrophic for that network. If you take out one neurons or modified one output of one neurons and to add some noise to that kind of neurons, what you will get is catastrophically end in that network.
But with that, you can add actually like some noise to the spiking one, and it can be resilient. Yes. That's very interesting. Because like again, I don't have that full understanding of these things, but from what I hear, like I talked with Randy Ellis about machine learning a bit from my previous podcast, that with machine learning models, they can be sort of prone to like they can do one thing, but then you start changing. Like say it's trying to figure out like, you know, cats and it's trying to identify them, but then it can sort of be, you know, prone to like then sort of failing in other tasks. So maybe in the future, would you say that there's like a potential to like be more resilient in like these kinds of tasks? Am I like just in general, like if we try and like we're trying to predict things, we're trying to produce algorithms that play games, do you think they could be more resilient to and better able to generalize? Is that a reasonable thing to say?
Yes. Yeah. First of all, that was a good podcast with Randy. I will actually love it.
Thank you.
And yes, I think we are able to produce the same level of accuracy with the spiky neural network. The problem with both of those aspects is I'm not sure currently now it's under real debate, and how can we interpret the result? Can we unbox the black box in a way to understand why exactly the network decide to use this decision or to make that decision or not the other? It's really hard to make that in both categories of neural networks. So I'm not sure that that aspect will be solved out, but other aspects I'm sure that the direction of spiky neural networks are much better approach.
Interesting. Would you say that like in both approaches, like sort of irrespective of which one, there is like a problem where it's we can allow these, like for example through back propagation we can do things in machine learning to help the network learn, but again it's kind of black box, it's hard to actually know why or how it's working, whereas in right, interesting. Whereas in biology, we assume there's like a rhyme and reason to it, right? And we could even like in theory have different machine learning models modeling the same thing, and in a way they have completely different weights or different ways of doing it. Then we don't know how it does it.
Exactly.
That's
so in a way, there are some rules that we understand from biology. So, for example, Hebbian learning. For spike together, wire together. That's one of the Hebs rules that are postulated already something like 40, 50 years ago. And we still use that kind of rule in spiky neural network. There are many other rules like long-term potentiation, long-term depression, that are use some sort of spike trend to depress a network or depress a synapse, or make the synapse more stronger. And other rules like spike time plasticity, those are kind of rules that we use today. But using all of those tools, we're not getting near the potential that the network have in performance. And how do you know that? For example, is if you take the same neural network, build the same architecture of spiky neural network and the artificial neural network, train the artificial neural network with backpropagation, because that's the way that to know today are the fastest and best the way to train the neural network, and try to copy the weights with some modification manipulation. It's not one-to-one copy, but copy the weights to the spiky neural network. You can produce the same output. You can use the neural network, the spiky neural network, to operate exactly as the artificial neural network works. So for me, that kind of experiments say that there are weights, exist weights that can operate in spiky neural network. We just don't know how to reach them. And our understanding in neuroscience is not enough to get to that point. But that's what we need to understand with the biologist, and in order to improve that kind of aspect.
I'm picking up on something here, which is that if biology seems to correspond more to spiking neural networks, but from our perspective, like we don't actually have effective ways of actually getting them to learn through spiking neural networks. We kind of have to like first use the more typical neural networks that we've used before. But I'm interested because biology assumedly has ways of learning through them to the degree that we can model them. And so it's very interesting. Like, do you think that we could try and learn from biology, and let's see how is it learning using spiking neural networks, or these kinds of things, and then might we then try and think about how we could apply those to spiking neural networks as we use them? Does that make sense?
Exactly.
So very interesting.
Yeah,
it'd be interesting if we could find these out.
It makes a lot of sense, and that's actually the main active direction that's been done in the neuroscience community. How neurons change their behavior, what governs those change, how those change happen, what kind of rules to make the neurons connect or prune the connection or to modify the connection between each other. That's active, very active subject in neuroscience. That
Mm-hmm.
every direction, every bit of new information in that field will spark all the development in any other
Uh-huh.
fields.
Very interesting. Like on this topic, I think it might actually be cool to talk about you think you worked on a paper where you used bioelectric networks or bioelectric potentials of cells, and maybe you can explain that too. But they're very complex, and they on wide scales and large complexity in biology, they help do things. They can help regenerate parts of organisms, but it's hard to predict and understand like what mechanisms, like how it's actually how the patterns correspond to the complex things they do. And I guess my question is, what in what ways could are we trying to use spiking neural networks to like try and understand that? What are the problems and issues, and why would we want to try and understand how something like that works?
Oh, okay. So this is completely different, sort of
Okay.
different topic. This is now we're touching what I'm doing now in the Levin lab,
Okay.
and you're referring to the bioelectric paper that was come up recently
Hmm.
with Professor Michael Levin. So in a way, let me just make a little bit in introduction. Um, Spiking neurons or the nervous system are not much different in any other cell in our body. In a way, neurons are one specialized case of any other cells that you have in a body. They all started as a stem cell. They start with a stem cell and start to differentiate and start to specialize in one kind of cell. In the way, spiking network have some properties that other cells doesn't have. For example, they have threshold. Skin cell, for example, doesn't have threshold,
Mm-hmm.
but both of those cells have ion channels, have genes, have the same infrastructure that cells have.
Mm-hmm.
Neurons, for example, have different connectivity. They connect from a lot of other neurons, not only in their surrounding. Then there are also the many ways that they can be getting information. They have the gap junction from smaller or closer neighbors,
Mm-hmm.
and they also have the synapses that getting information for far neighbors,
Uh-huh.
compared to skin cell, for example, that are much more closer and intact.
Mm-hmm.
So the only way that they're getting information is the neighbors around them, and
Right.
maybe a blood vessel that transmits some nutrients and some hormones and many other chemicals.
Right.
So in a way, the cell itself in regular cell, in a skin cell, for example, or any other tissue that's not neuron, getting a lot of information that they don't really know exactly where that information comes from. That
Mm-hmm.
there is no return address on the chemical that's being sent to that neuron,
Uh-huh.
so to the cell, for example. So the cell itself doesn't know where that chemical arrived, but it needs to make a decision based on those chemicals.
I
So
see.
in computer science, we can look at that problem as a cellular automaton. Cellular automaton is a sort of fictional creature that
Mm-hmm.
only that have a very simple rules, and they are based on those rules, based on the decision of the environment that it's been, and based on that information, it make his own choice and make his own pattern. So in the work that I did with Professor Levin, um, what we ask is how cells, if we would like to have some pattern in the cells, some electrical pattern in the cell, how can we convince the neurons to get to that to cells? So how to convince the cells to get to that configuration? And the way we use a genetic algorithm, again, another algorithm that being completely inspired by biology. genetic algorithms that use parameters as a gene and try to manipulate the parameters the way similar to how we manipulate gene in cells or in mutation. They have mutation, crossover, copying, exactly as sexual reproduction in genes. And we use that algorithm in order to find the right combination of the ion channels that every cell in that tissue contain. So based on that ion channels, so every other neurons contain the same blueprint, the same configuration, the same instructions, but we start in different configuration. And when we see the patterns arise and build up, using that configuration, similar like cellular automaton do. And we use that genetic algorithm to pinpoint or to make a tool and in a way to say, if a biologist would like to have this kind of pattern, we give to the machine the end target and say, find a pattern, find a configuration that will end up like that. And it takes a lot of time, but it find the right configuration to be the way that we would like that the electric pattern will be.
I see, I see. To help me understand this, so one thing you talked about was neurons, in a way that they're more similar to other kinds of cells than we think. And one interesting thing, am I right in saying that with neurons, like they have more, they have direct connections such that they know where messages are coming from, whereas with cells in the rest of the body, say, like they're using more chemical messages, so they're more having to like make decisions, like, okay, they don't know exactly where it came from, but at a certain point they need to make a decision,
right,
but they don't know exactly. And in what way is that relevant to what you were just explaining in trying to understand the sort of the pattern that you want to get in the say like the cells that you're working with? Because like the way I'm trying to understand this, like why would you want to get like a certain configuration of like the way the cells are working? Why would we want that?
Oh, so in a way, neurons are not, as I said before, it's not really different than regular cells. The only different is that they have other ways of input. But the old ways of communicating between other cells already exist in the cell itself, and they are not far from that advancement. So it's not really far advancement from the regular cell. So every what you can learn from regular cells probably will be applied the same way to the neurons. It may be different manipulation or different time scales, but the same principle will be valid to the neurons. So neurons, for example, doesn't only make the decision based on the input from the synapses. They also have other inputs. They also have the next cells that they're connected to, and they have the blood vessels that transmit a lot of other information. So those already exist in very similar or simpler cells, like a skin cell, for example.
And like am I misunderstanding this, but can we like learn in the configurations and the like through bioelectrics and chemical messages in normal cells, can we learn more about how neurons work from doing that? Am I right in saying that? Is that something, or am I sort of misreading
that's our hope? Yes, that's our hope, exactly.
That's what you want to do. Very interesting. And like you were trying to make like a machine learning as some sort of like reinforcement network that sort of learns how can you get the configuration of, I guess, bioelectrics and like, so there's certain configurations that allow the cells to do certain things, but it's just like, why is it difficult to learn that, and have people tried to like model these kinds of things before?
Oh, so that's actually an important question. our cells, our simulation of cells, especially in that paper that you referred to, is very simplified cells. They only have the current configuration. They doesn't have the mechanism or the transcription of the genes that are responsible to the process of how many ion channels exist in the cells and what to do if there is some information coming, what ion channel configuration I need to change and manipulate. In our simulation, our cells are very dumb. They are fixed. They are always have the same number of ion channels, the same number of gap junctions, and they're in the way that being configured are fixed throughout the simulation. So once we add more complication, like for example, the GRM that responsible, the gene regulatory system, that responsible to modify and to adapt the surface of the cell, it make the cell itself much more smarter creature in a way. So it already have now a program that's saying, if I'm getting this kind of information, that's what I should do. And there is that program manipulate the way the cell is interact with the environment. So in this paper, we assume that we peel off that smartness, and in order to make our life simpler, if we put it in, they make a lot of other variables that it's hard to control. But assuming that we can control on all of those cells at the same time using that genetic algorithm that we created, we can find that kind of configuration that create that pattern. Therefore, our assumption is that the GRN do the same thing in much more clever way.
I see. Like from here, I kind of want to ask sort of a more stepping back a bit, a kind of broader question is, I'm wondering, given we talk about like the way we have to necessarily simplify things to model them, what like in both maybe the near term and the longer term, what do we think are the limits, and where do we think we can get in terms of modeling things? What could we do if we have more computational power, and also how close could we get to actually what biology does, if that makes sense, replicating it?
That's a good question. I think I don't know how to make prediction on the future, but I can tell you that in the last 40 years, we end up to have more computational power in our fingertips than ever we can dream of 40 years ago. So the supercomputer of 40 years ago is almost equivalent to your cell phone now that have 18 cores and 16 gigabytes of memory. This is something that we didn't dream of. And look at the way that we currently now simulating things. So if the current way of computational power continue in this direction, we will end up having more and more complicated simulation. And the way that's actually almost philosophical question, how low we should go. We don't really know, but it's actually depend on the question that you ask. If you ask on the way that chemical interact with each other, we need to go very, very low level. But if you would like to say, okay, I don't care about the level of the way that chemicals interact with each other, the fusion reaction between cells, I would like to have the operation, like what happened if that neuron spike or that transmission happens, and so you can simulate in various different levels. So either we go deep or we go wide in simulating much more, many more neurons, many more cells, and create organ tissues.
Oh, if I am I right in understanding it? So you could imagine we might use the same sort of technologies we use now, but just simulate many more at the same time, and in that sense make it more complex. Or you could like make an individual neuron more complex, but like with the same computational power by necessity, you'd have fewer of them. And so there's two kind of ways that you use more computational power. Is that right?
Yes,
Yeah,
exactly.
that's
Exactly. It's all depend on how much computational power you have and what the question you will
right.
ask.
Very and like on that note, I'm wondering if we have more computational power, like, and you talked about how we might ignore the number of gap junctions a cell has because it doesn't matter. Do you think that maybe we'd be able to like find out parts of biology we thought didn't matter, and we could simplify it, but then we can like maybe find out actually no, we realized that this was more important than we thought. And when we have the ability to model it, or when we try and take it into account, maybe we does that make sense? Maybe we realize through taking into account more complexity and trying to model it, might we realize that it matters more than we thought? Does that make sense?
It, you're talking to the choir, like, because I'm the computer scientist. For
Okay.
me, simulation is everything. For me, if I cannot simulate what I'm thinking it's operate, and if the simulation not but doesn't produce what I think it should produce in reality, that's mean our understanding in how things work is incorrect, and we should improve our simulation.
Hmm.
So in a way, if we cannot simulate it, it's not working. It's not. We don't understand it correctly.
Right, right. So we need to understand it first before we can apply a computational sort of models to it, right? Am I right in saying that? Or, but,
And we need to check our understanding, meaning
mhm.
in order, if we think that we know how things work, we need
Right.
to check our understanding by simulating. And
Uh-huh.
if the simulation behave as we expected it to behave, we may have the grasp of the idea. But if it's not working as we expected, therefore something in our understanding is lack. We lack some understanding, and that's what we're missing. And we need to experiment and find those rules.
Right.
Similar to what I described before, that I said taking a spiking neural network in our current understanding of weight adaptation, in how weights or connection adapts in nature, in
Mhm.
nervous system, is not enough to make a simple a simple task like a neural network currently work. But we know that if we train a neural network in our mathematical way, in produce already, we come up with the right weights. We can take those weights and plug it in to the spiking neural network, and it will work.
Uh-huh.
Therefore, for me, it's saying we are lack of something. There are something missing in our understanding how the neurons or the spiking neurons adapt to the input and
Right.
learn in order to reach to the same performance. So
Right.
I'm using the artificial neural network as the gold standard to what I can do with spiking neural network.
I see. I see. And as and it kind of touches on what we talked about earlier, right? And like biology must have ways of doing it, and so you're talking about as well, like computation and modeling is a way we can also help us understand things. It goes both
Right.
ways. We don't just do what we know. We need to test what we know using it. Interesting. Um, well, like again, like kind of coming to the end here, but like one question I want to ask, maybe you'll find it annoying. But I was thinking about like humans and like to what degree, okay, maybe we're trying to model ourselves and we're using computational. Um, like I was thinking, to what degree do you think does it degrade humans or degrade like the complexity of life if we can like try and model it using computers, because sometimes it can feel, oh, is it like lifeless? Oh, if we can model something, is it just a simple algorithm? Does it make it less important? I don't know if you have any thoughts on this. given that you spend much of your life working on these kinds of computational issues?
That's very hard philosophical question. That's our definition of what life means and what one reality means. Does ChatGPT conversation is real and there is some understanding beyond that? I'm sure that if you take the conversation from ChatGPT and show that to Alan Turing, I'm sure that he will love that. And I'm sure that he will come up with a completely different way to test his theory of the Turing test. I think what we are in the stage today that we need to question our understanding of what consciousness, what being alive mean. If we have that kind of machine that we know how it works, we know that in a way, it's not conscious that in a way that we perceive ourselves, but it's at least have the capability to fool us that it's enough knowledge or enough life.
Right,
So I think it say about our understanding a lot.
And a third thing I wanted to ask is, because you mentioned ChatGPT there, when we have say with ChatGPT, like you have many layers and billions of weights and things, in a way you can say, oh, we understand it because we can like see the weight, so in a way we know how it works. I'm wondering, like, to what degree, we mentioned it again sometimes in the podcast, but to what degree do we not know how it works? To what degree do sometimes we're doing things and we're actually kind of completely in the dark, and like I'm just wondering what you think of like black box, when it becomes, when you don't actually, you can see it all, but you don't really know how it works. What are there problems with doing that when you like don't really know how it works, but you just have loads of complexity? Does that make sense? Like, is there any other approach?
There are many things. There are many things today that we don't really know exactly how they work, but we're still using them. So in a way, you look at it as a perspective of engineering. I don't need to know exactly how it works. I just need to know what will happen if I modified it in certain degrees, in some boundaries that I required to operate. So depend of the perspective of the question. If you're going to use it as a tool, I don't see what's wrong with that. But if you would like to use it as a tool and as a decision environment, I will question that decision to use that kind of tool, because we are not really sure what exactly operates there and what makes that decision, and how you can trust that the next iteration or the next experiment that you will do, you trust the system to do the same as you obey it to do, or you hope it will be doing.
Right. So there's different ways you can use the technology. So you might not want to use it to, like, since you don't know how it works, you can say, oh look, it's like us, has consciousness, right? But it's like, well, okay, we don't know the mechanisms behind it. So sometimes we, like in the work you're doing, we might want to like sort of trying to figure out, like, actually, can we map it more precisely to like biological things? Very interesting. Well, I've really enjoyed having you on. Is there any last things you want to say, or like where people like could find your work or anything like this?
You can find my work just by Googling my name. My name is pretty unique, Hananel Hazan. I have a website. That's my exposure to the real world. And I love emails from any kind. So send away any emails with questions that you would like and talk or suggest. I would love that. Yes, thank you for having me here.
Yeah, awesome. I might be emailing you, asking more things because I learned those, and there's still things I wanna explore. Okay, awesome. Yeah, thank you very much. I'll start recording.
Thank you.